Pongola Ice Age. The earliest discovered so far is the Pongola glaciation, occurring about 2.9 billion years ago, which it's also the oldest known glaciation on the planet. Glacial deposits from this time have been found in the Pongola supergroup of Witwatersrand, South Africa from this period of time. There is no consensus on what may have caused this glaciation. It may have ended with increased tectonic activity and volcanism that accompanied the breakup of one of the very first supercontinents, Valbara, composed of cratons from South Africa and Western Australia, two of the few cratons that likely existed during that time, around 2.8 billion years ago. Ilya Bindeman and colleagues measured levels of oxygen isotopes in sandstone and shale samples from the Pongola supergroup, finding they had the lowest levels of oxygen-18 of any similar deposits analyzed so far. They also had very high amounts of oxygen-17, indicating the rocks formed at colder temperatures. This means ice, says Bindeman. Couple that geochemical evidence with the moraine evidence, and it means glaciers, the oldest glaciers yet found on Earth. Even if the climate of the Archean is not well known, the study of the oxygen isotopes seemed to show that the climate of the Archean was warm, or at least temperate, in particular due to high levels of methane and carbon dioxide in the atmosphere. A glaciation around 2.9 billion years ago is therefore likely to have been caused by a drop in the rate of these greenhouse gases. Huronian Ice Age. The second ice age, called the Huronian glaciation, occurred between 2.4 and 2.1 billion years ago at the onset of the breakup of the second supercontinent, Kenorland. The Huronian glaciation plays a crucial role in understanding Earth's climatic evolution and the transition of the atmosphere, particularly with the emergence of oxygen-producing photosynthetic organisms. The Huronian glaciation significantly influenced Earth's climate by creating extensive ice cover that likely led to lower global temperatures and altered weather patterns. As glaciers expanded, they affected sea levels and potentially created conditions that favored the emergence of oxygen-producing organisms, setting off a chain reaction that ultimately changed the atmosphere. The Huronian glaciation and the Great Oxidation Event are closely related in that both were pivotal moments in Earth's history regarding atmospheric changes. The glaciation may have created conditions conducive to the proliferation of cyanobacteria, which were responsible for producing oxygen through photosynthesis. As these organisms thrived, they increased atmospheric oxygen levels, leading to the Great Oxidation Event. Thus, the glacial period not only impacted climate, but also facilitated major biochemical transformations on Earth. The long-term effects of the Huronian glaciation shaped both geological and biological evolution. Geologically, it contributed to the formation of distinct sedimentary rock layers, like banded iron formations, that provide insights into ancient oceanic conditions. Biologically, this glacial event created a selection pressure that paved the way for more complex life forms by fostering an environment where photosynthetic organisms could flourish. Snowball Earth came to an end as continued tectonic activity and related volcanism from Kenorland's breakup caused a buildup of greenhouse gases, and new oceanic areas enabled circulation of warmer waters into the polar regions. Cryogenian Ice Age. The third major glaciation was the Cryogenian. This occurred during the breakup of Rodinia and was contemporaneous with an important stage in the formation of Avalonia. There were two significant glaciations during this time: the Sturtian from about 715 to 650 million years ago, and the Marinoan from about 650 to 635 million years ago. During this time, the bulk of the continental masses were assembled near the South Pole, and disruption of oceanic and atmospheric circulation may have triggered these ice ages. After the long environmental stability during the Boring Billion, the Sturtian glaciation began at the beginning of Cryogenian, freezing the entire planet in a state of severe icehouse climate known as a snowball Earth, and is the longest and most severe known glacial event preserved in the geologic record after the much earlier Huronian glaciation. After 70 million years it ended, but was quickly followed by another global ice age, the Marinoan glaciation. During the Marinoan glaciation, characteristic glacial deposits indicate that Earth suffered one of the most severe ice ages in its history. Glaciers extended and contracted in a series of rhythmic pulses, possibly reaching as far as the equator. Between the Sturtian and Marinoan glaciations was a so-called Cryogenian interglacial period, marked by relatively warm climate and anoxic oceans, along with marine transgression. The ending of the Marinoan may have been precipitated by the renewed tectonic activity and volcanism that led to the breakup of Rodinia. Significant volcanic activity in Avalonia occurred during the end of the Marinoan glaciation. Andean-Saharan glaciation. This was a regional event that appeared to affect mostly continental areas that were near the South Pole at the time, and happened between 460 to 420 million years ago. The Andean-Saharan glaciation is widely considered to be the leading cause of the late Ordovician mass extinction, and it is the only glacial episode that appears to have coincided with a major mass extinction of nearly 61% of marine life. Estimates of peak ice sheet volume range from 50 to 250 million cubic kilometers, and its duration from 35 million to less than 1 million years. During the Andean, the Ice Age is believed to have been significantly more extreme than the last glacial maximum occurring during the terminal Pleistocene. Glaciation of the northern hemisphere was minimal because a large amount of the land was in the southern hemisphere. Researchers believe that ice sheets began to form over the present-day Sahara Desert across Morocco, West Africa, and Saudi Arabia between 450 and 440 million years ago. Geologists have not yet reached an agreement as to how this particular ice age occurred. For example, researchers agree that the strength of the sun was weaker at the beginning of this time period, and that this weakened solar energy could possibly prompt a period of glaciation. However, the amount of carbon dioxide in the air was at extremely high levels, meaning high temperatures on Earth. Karoo Ice Age. Occurring from 360 to 255 million years ago, this glaciation again occurred on continental masses located at the south polar region of the Earth. During the earliest part of this ice age, scientists believe that ice sheets grew from the southern region of both present-day Africa and present-day South America. Most theories of how this ice age was first created are primarily rooted in the knowledge that plants on land began to undergo significant evolutionary changes during this time. As these plants grew to immense sizes, they worked to reduce the levels of carbon dioxide and increase the levels of oxygen in the atmosphere. As these changes occurred, the summers were not warm enough to melt the ever-increasing ice sheets around the world. The major effect of the Karoo Ice Age is the increased evolution of plants and animals during this time. As oxygen levels increased, animals began to experience changes to their metabolic systems. As a result, large vertebrate, both land-roaming and flying species, were able to evolve. Quaternery Ice Age. The Quaternery Ice Age is the ice age that is currently being experienced by Earth. This period of glaciation began approximately 2.58 million years ago and is characterized by the expansion of ice sheets over both Greenland and Antarctica. As these ice sheets have grown, the amount of sunlight reflected back into the atmosphere has also increased, resulting in cooler temperatures across the globe. Several theories explain the Quaternary glaciation, including changes in ocean currents, tectonic plate movements, and other climatic and geological factors. The current ice age has had a massive effect on the general geography of the surface of the Earth. The erosion and sedimentary deposits caused by these glaciers has been instrumental in the creation of large mountain ranges, deep river valleys, and lakes and rivers. The cool temperatures of the Quaternary may have allowed our brains to become much larger than those of our hominid ancestors. Neanderthals may have struggled to survive as the rising and falling ice ate away at their habitat. What is beyond doubt is that Homo sapiens survived and turned to farming soon after the ice retreated. As the last glacial period ended, two major cold snaps occurred. The older Dryas, 14,700 to 13,400 years ago, which turned much of Europe into tundra, and the more severe younger Dryas, 12,800 to 11,500 years ago, likely caused by glacial meltwater disrupting ocean currents or possibly a comet impact. Around 12,000 years ago, with the start of the current interglacial period, the Flandria, the ice sheets retreated, allowing humans to repopulate northern regions. The interglacial pattern of this ice age has been disrupted by human-generated carbon dioxide and methane, which is pushing the Earth's climate into a warming cycle when the climate should be cooling off. Thanks for watching this far. See you next time. Don't forget to subscribe to the channel if you liked.